In this example, what we're going to be discussing is the photoelectric effect. And what the photoelectric effect is let's say that you're going to have a material, so some sort of metal. You have a metal, and what you're going to do is you're going to radiate it with light. Typically, it's going to be some type of X-ray. And what's going to happen is an electron is going to be photoejected from the surface of this metal. Now, the surface depth is anywhere between 10 and 100 angstroms. And the electron that gets, if you remember that you have an atom, this is your nucleus, you have a row of electrons, you have more rows of electrons. The electron that gets photoejected is going to be a core level electron. And this is an amazing technique in which you can determine the surface of determine the surface of a lot of substances. For instance, you can characterize the surface. So the surface here might be slightly different than the chemical composition down below. And any chemistry is going to occur at the surface. I used to work at 3M a long time ago, and I would do this technique not on a metal but on adhesives. And the adhesives that I did this on were the adhesives that held body panels together on your vehicles. So your body panels are held together by, essentially, at that time, were held together by 3M double-sided sticky tape. That's really what it was. It's a little bit more heavier duty than that, and it might be something different now, but that's what held it together back in the day. All right, so the problem reads as such. If the work function of the photocathode is 2.4 times 10 to the negative 19th joules, what is the cutoff wavelength? So the work to remove an electron is going to be 2.40 times 10 to the negative 19th joules. That's what we're looking for. Now we know that energy is equal to h nu. Your book may use F for frequency. I use nu. I've always used nu. H is going to be Planck's constant. E is the work. That's going to be the work that's required. Now, if you remember, nu, we're looking for a wavelength. This is a frequency. Nu is equal to C upon lambda. So your work is equal to hc upon lambda. And what we're solving for is we're solving for the wavelength of the cathode. So our lambda is equal to hc divided by our work. Now we can plug into this expression now. So we have, I'm going to use a different color. We can use our lambda is equal to h is going to be Planck's constant, which is 6.626 times 10 to the negative 34 joule second. Multiply that by the speed of light. That's going to be 3 times 10 to the 8th meters per second, divided by, now, the work that we have is 2.40 times 10 to the negative 19th joules. And what we can see here now is that the seconds will cancel with the seconds, the joules will cancel with the joules, and we're left in units of meters. We do the arithmetic herein, and we get 8.28 times 10 to the negative 7 meters. And a lot of times when we're talking in units of wavelengths, we typically want to convert this into nanometers, and you would multiply this by 1 times 10 to the 9th, and that gets us 828 nanometers. And so the cutoff wavelength to photoreject one of these electrons is going to be 8.28 nanometers. If you have any questions on this or any other questions or any other problems in this chapter, please let me know.